about erasure coding, but the history of error detection and correction and how that led to erasure coding. So thank you for coming. And it's not working anymore. One second. Okay, there we go. Nice. Cool. So, who am I? So my name is Danny, and I work for Softiron in the UK, where we're working on building a Ceph appliance. I've mainly worked for open source companies in the past, so companies like Linbit and CodeThink, and I run a non-profit in the UK called Open Source Events, where we do tech meetups and conferences, mainly around OpenStack and Cloud Native. And yeah, I like beer. So I mainly got interested in this topic a few years ago after I saw a colleague called Jim MacArthur do a lightning talk on error correction. And so I wondered how this relates to RAID and other storage technologies. And I did some digging and figured out there's lots of ways to do this. And I thought I'd provide an overview of some of the ways that error correction and detection is done. So the main idea is to have a set of techniques so that when we're transmitting data, we can figure out if once we've received the data on the other end, it's inconsistent, or even better, if we can correct the data rather than just dropping it. So these concepts have been around since before modern computers were born, but they've come a long way, so even the older ideas are still around in some of our modern technology. So why do we have errors in the first place? It could be human error, it could be network glitches, it could be something more random, such as noise on a chip or cosmic rays interfering with the chip. All of these things can cause us to receive something different, or the data to send something different. So by a show of hands, how many people have heard of a parity bit? Pretty much the whole room. Cool. So the parity bit is the earliest and most basic form of error detection in computers. And it's a very basic type of checksum. And the idea is that you can add a bit to the end of a set of bits, which let you detect an error when you're transmitting the data. So we do this by adding up the number of 1 bits we have. And if it's an even parity bit, then we make it true for an even number of 1 bits. And if it's an odd parity bit, we'd make it true for an odd number of bits. So you can see here that in the first character, we have 2 1 bits that we're transmitting. So because that's even, we'll add a 1 on the end and we'll send that. And if we receive the same thing on the other side, we know that no error has transmitted. Same again with k, an even number of bits. So we add a 1 on the end. That's the one in bold. And if we transmit it and there's an error, or there's a different number, we can do the calculation on the other side and see that actually we should have a 0. There's obviously some sort of mistake. So we just drop that frame and ask whatever sent it to retransmit it. And same again on the third one, there's another error there, and that's an odd number of bits. That's why the last bit that we're transmitting is a 0. So this concept goes back as far as the 50s, and we had parity tracks appear on mechanical tape drives in the early 50s. The major flaw with this is that if you have more than 1 error within a byte, we're not going to detect it. So it will only pick up 1-bit errors. So if there's multiple bits within the same segment, then obviously it's going to be a false positive. It's still very useful though, and we use it quite heavily in hardware applications such as microprocessor caches, the PCI and SCSI bus standards, and RS-232 serial, and lots of other hardware applications use it. So that's a very simple way to detect basic errors in transmission, but we can't correct them. There's a decimal equivalent to this. And this is used in lots of different real-world applications, like social security cards, ID cards, and all major credit cards. So this is one of my old credit cards or debit cards. And you'll see that the last digit is actually a check digit. So how does this work? I don't know if you've ever noticed that when you're putting your credit card or debit card number into a web form, it might automatically know whether that's valid or not. Even if you're not connected to the Wi-Fi, it's all happening locally. And that's due to this Loon algorithm. And so the idea is this guy, German-American engineer, worked for IBM in the 40s and 50s, and he was the first guy that came up with the idea of information buckets to speed up data retrieval and storage. And the idea here is that that he came up with this algorithm is that you double every other digit starting from the right, and then sum all the digits, and they should be a multiple of 10. And if they're not, then you know that something's wrong. So the last digit will either make it a multiple of 10 or it won't. Cool. So then we get on to trying to do some correction. And one of the main pioneers here is a guy called Richard Hamming, and he was a mathematician and professor who worked at Los Alamos on the Manhattan Project in 1945. And he was on a team which was responsible for programming the IBM calculating machines, which had the scientists' formulas, check that they were correct. And a few years later, he went on to join Bell Labs, and he became known to be one of the Young Turks, who was a group of people at Bell Labs that all had heavy contributions to computer science. They were all pretty well respected, and they weren't given the usual responsibilities and structure, but measured by grants and teaching and papers. They were kind of just left to get on with it. And 3 of them ended up going on to win Nobel Prizes, and a few of them went on to lead Bell Labs. But all of them are highly respected scientists. John Tukey was one of the first guys to come up with the term bit, which is contracted from binary information digit. So while he was at Bell, Richard Hamming set one of his calculating machines to work on a problem over the weekend. He set it on Friday, and when he came back on Monday, he discovered that due to an error, the whole calculation had died early on Saturday morning, and so he'd have to restart the whole thing again, waste 2 days of work, or wait till the next weekend. And this was quite common because you had punch cards, and so if a card was bent or it didn't punch properly, then you're going to have an error. So he then basically went on to perform probably the biggest yak shave in history, and decided to sack off all that physics nonsense and figure out how to get calculating machines to detect errors and automatically retransmit data identified as inconsistent. So he published this key paper in 1950 called Error Detecting and Error Correcting Codes. And he described a few concepts that are still core to error detection and correction today. And these are, number one is the Hamming distance, which just describes how many single-bit operations I have to do to correct a binary number or string. So, for FOSDEM 19, FOSDEM 20, there's 2 characters different. That would be 2, but obviously on a binary level. This can also be represented geometrically, and it's called the Hamming cube. So he went on to define this system called the Hamming codes, which is far more robust at checking errors than standard parity. And what he developed was the concept of having 3 parity bits for every 4 data bits, which is quite expensive. But it means that we can detect errors up to 2 bits and also correct 1-bit errors. So how does this work? Let's have a look. So if we have 4 bits here, D1 to D4, and we want to send them over some sort of transmission channel, we can arrange them at the intersection of 3 circles. So 1, 0, 1, 0. And then we can calculate the parity for each circle. So for parity circle 1, we have 1 1-bit, so that's an odd number, so the parity will be 0. For parity for the second circle, we have 2 1-bits, so that's even, so parity is going to be 1. For the third circle, we have, again, 1 parity bit, so that's odd, so that's going to be 0. So we have 3 parity bits, we add them to our data, and we send that across the channel. Now, on the other side, we receive something different, so we get a D3 is turned to a 0 instead of a 1. So how do we detect this in the new circle that we're arranging on the other side? You'll see that D3 switches to 0, and then we'll recalculate, starting with the first parity circle. Nothing's changed there. It's still an odd number. Something has changed there. It's now supposed to be an even number of bits, but it's not 1 bits, but it's not. And the same for parity circle 3. So we know that the offending bit is at the intersection of the second and third circles, so therefore it's D3. And so we can just flip that bit and correct the error. So that's the basic way that Hamming codes work. So we use parity pretty heavily in RAGE. Some of you will be familiar with RAID levels. You probably haven't come across RAID 2 because nobody uses it, and that's because it's really expensive. But this is Hamming codes, and it happens at the bit level. And so you can see that there's 4 data blocks and 3 parity data bits, and 3 parity bits for that are striped across these hard drives. So yeah, I don't think anyone uses this. Then you have, obviously, I'm sure all of you are familiar with RAID 5. RAID 4 is similar to RAID 5. The only difference is that rather than distributing the parity bits across the drives, we put all the parity bits on one drive. And that means that writes are slower with RAID 4 since there's less data drives to write to. But since all the parity is written to the same disk, random reads are better. So writes are slower because the parity has to be written to the same disk, but random reads are better because there's less disks for you to look for because you have a dedicated parity disk. So that's RAID 4. This is RAID 5, and you're all familiar with RAID 5, I guess. The way it works is it runs an exclusive OR on the block. So for every 2 blocks that we write, we run an exclusive OR, and then we write the result as a 3rd block. And so green here is the parity data. So if I keep doing that, and obviously on different drives, I end up with a whole bunch of data. Now, if I lose one of the drives, I can recalculate it. It's really simple. Just run exclusive OR again on the other 2 data blocks, and I can regenerate that drive. So that's how RAID 5 works. So that's Hamming codes. That was in the 50s. Then these guys came along in the 60s, and they changed everything. Gustav Solomon and Irving Reed. And these guys were staff members at the MIT laboratory, and 10 years after Hamming's paper, they published a paper called Polynomial Codes over Certain Finite Fields. So I was reading up on this, and I suddenly realized that this was getting really mathematically complicated. I'm not a mathematician, and I was out of my depth, so as I always do when I'm out of my depth, I go onto IRC and ask a question. So I did that. I went looking for the right IRC channel to ask it, and thinking that this would be helpful. I knew there was a bunch of mathematicians on this channel, so I just asked, can someone explain polynomial interpolation to me? This is the response that I got. I don't know, maybe some of you understand what that, I have no idea. But yeah, I need to stop going to IRC as a resource. The main idea behind Reed-Solomon does, however, revolve around this concept of a Galwa field. Galwa field, it's named after Évariste Galois, who was a French mathematician, and unlike our previous heroes, had a much more troubled and interesting life in the sense that he got interested in maths at the age of 14. He published a number of papers by the age of 17, of which one of them was about Galois fields and Galois theory. And this was a year after he was rejected from university because his examiner couldn't follow his train of thought and was very confused. He was politically active, ended up in prison a number of times before he engaged in a duel to the death with an officer at the age of 20 and died. So not the most glamorous of stories, but yeah, he did define this concept called the Galwa field, which is basically a mathematical field is a set of numbers which you can conduct mathematical operations on, and a finite field, or Galwa field, is one that is finite and is always the size of a prime number or prime power. And these fields wrap around, so you can conduct any operation on the values within the field and always get another value in the field. And you do this, you can just modulate the size of the field once you get your results. So this can contain numbers, it can contain polynomials, and it can contain roots of polynomials. And how does this relate to erasure coding and error correction? Well, the idea is that using a Galwa field, you can essentially plot any sequence of data as points on a polynomial graph. And that's because the graph itself is representative of the Galwa field that you're using. Once you've done that, you can then find other points on the graph which you can use as parity data. So the purple ones are other points that we found on the same graph. And that's what we will use as our code shards. And the idea is that you define a code and you use that on both sides to recover data. And it's highly efficient, but much more computationally expensive. So here's an example. K is the number of data shards that we have. M is the number of code shards. On the left, we have what's called a distribution or generator matrix, which is made up of an identity matrix at the top, which is essentially is equivalent to 1. And then the bottom piece is the code shards, which we generate. So we add them together and we multiply that by our data, and we end up with a set of data and a set of parity blocks. So let's say we lose some of our data, the bit in K. We can replace those with C1 and C2, which are what we ended up calculating, and we can multiply that by the inverse of the same generator matrix that we have, and that will give us our data blocks back. And obviously that's far more efficient than using something like the Hamming codes. So this is really, really popular. It's one of the most popular error correction codes we use today, and it's seen everywhere, including CDs, DVDs. It's using 2D barcodes as well. So any 2D barcode that you scratch or is damaged can still scan because it's using Reed-Solomon to recover from that damage, and it's also used for generating QR codes. So most implementations of RAID 6 also use Reed-Solomon as well. So this image is taken from the Erasure coding docs in Ceph, and it's specifically for K equals 3 and M equals 2. So 2 parity shards for every 3 data shards. So in Ceph, when you create a new pool, you specify if you want it to be Erasure coded or not, and also which Erasure coding algorithm you want to use. Ceph has a pluggable architecture for Erasure codes, so you can specify which code you want to use on a pool-by-pool basis. Once you've chosen an Erasure code, you can't then change it for that pool because you'd have to obviously recalculate everything. So you need to make sure the only way to get around that, you'd have to create another pool and migrate. So if you're going to use an Erasure coded pool in production, you want to be sure that you've chosen the Erasure code that best suits your workload. Almost all of the Erasure coding plugins within Ceph rely on some form of Reed-Solomon. There's a number of different varieties, though, with different strengths and weaknesses. The main plugin that's used in Ceph is called Erasure, and that has both Vandermonde and Cauchy versions. Those are both versions of Reed-Solomon, and they differ just in how you generate the matrix at the beginning. There's also some more recent propositions. There's one called the Shingled Erasure code, and that aims to be more configurable and more efficient. There's also an implementation called Clay, which focuses on reducing network bandwidth, and there's one called Locally Repairable Codes, which specifies another variable called L. So you can say, I want my parity blocks to be stored in a specific geolocation, which helps us recover from erasure coding damage, but without straining the network too much if we have a geo-replicated multi-site Ceph cluster. So yeah, the key thing to remember is choose the right numbers for K and M, obviously depending on how much storage you want to use, how much it's going to cost you in storage, and also pick the right erasure coding plugin once you've done some testing with your workload, so you know that obviously it's a kind of more final choice. So how does this relate to our work at SoftIron? Well, we're working on building Ceph appliances, and there's lots of operations that we want to do in Ceph which are computationally expensive. Compression, erasure coding, and encryption are all examples of this. So we're working on defining some of these algorithms in hardware so that we can use FPGAs to do the heavy lifting for us and keep our CPU usage to just Ceph. So yeah, that's my talk. Anyone have any questions? No mathematicians in the room, I guess.
I read that performance was error performance was really different between the K and M's you choose.
Mm-hmm.
I read it should be multiple of 2, or maybe something. Can you explain why and which combinations may be the best?
So I think the most commonly, so the question is, what combinations of K and M are best, and how do they affect performance within Ceph? So typically we see people using 6K and 3 for M, or 9 and 4. Those are the most commonly used ones. We're only implementing a few different combinations on our FPGAs for that exact reason, because each one is going to be different how you define it in hardware. So I think there's a standard set that are used. And yes, if you try and do it with less M, then you're going to have to do, it's going to be much more expensive to calculate the number of M as a proportion. So you want to use a ratio of about 3 to 1, I think. Koen.
How does the distributed nature of Ceph affect the acceleration? Well, I imagine there's network latency.
Yes, there is network latency. So there is heavy network latency in Ceph, and that means that, so the question is, how does it affect, how does the distributed nature of Ceph affect acceleration? So there is network latency in Ceph, and that means that in some cases, the cost of going to recover the data in time might be still far less than the expense of doing the replication over the network anyway. So you kind of have to have a bit of a cost balance and figure out in which cases it might be worth not accelerating the process, in which cases it might be worth accelerating. So it's a trade-off, and I think in some cases it is, some cases it isn't, and that's a very important factor in deciding whether or not to accelerate. Does that answer your question?
Yes.
Cool. Okay. Well, thank you very much.